So in the previous class, we have discussed Euler's equation and examples of Euler's equation. And today's class will discuss few more examples on this Euler's equation. So go on to this next example. Find the extremal of the functional integration from x1 to x2 y dash raised to 2 minus y square plus 2y sec x dx. Means we need to find the extremal of this functional. So first, f of x, y, y dash means a relation between x, y, y dash. So this is y dash raised to 2 minus y square plus 2y sec x. We have Euler's equation dou f by dou y minus d by dx of dou f divided by dou y dash. This is equal to 0. So this is a Euler's equation. So first find dou f by dou y. So dou f by dou y means differentiate partially with respect to y. We need to keep other variable x and y dash as a constant. So according to that, this is constant. Differentiation of constant is 0 and 2y and y square differentiation is 2y. So this negative sign, so minus 2y plus 2 sec x y with respect to y is 1. So this is dou f by dou y. So differentiate partially with respect to y dash. So while differentiating partially with respect to y dash, keep other variable x and y as constant. So this is constant, so 0, and this is constant because sec x is there, y is constant, this 2 is constant, so 2y sec x is constant. So left with what here? Y dash raised to 2. So differentiation of y dash raised to 2 with respect to y dash is 2y dash. So substitute these two in Euler's equation. So minus 2y plus 2 sec x minus d by dx of 2y dash. So this is equal to 0. And here 2 is common for both the terms. Take 2 commons and send this from LHS to RHS. So 0 into something will be 0. Next step is this minus y plus sec x minus d by dx of y dash is derivative of y dash is y double dash. So d by dx of y dash is y double dash. So this is equal to 0. Now take this sec x from LHS to RHS, plus becomes minus. So next step is minus y double dash minus y is equal to minus sec x. So minus is common for both sides, so cancel. So you will get here y double dash plus y is equal to sec x. So this is second order ordinary differential equation. So we need to solve this for y. So to solve this, we need to apply method of variation of parameter. So first, y double dash means what here? D square y by dx square plus y is equal to sec x, right? So first, this is a non-homogeneous equation. Solution contains two parts. So general solution is equal to complementary function plus particular integral, right? So we need to apply here method of variation of parameter. So auxiliary equation is m square plus 1 is equal to 0. M square is equal to minus 1. So minus 1, we may write this, we can write this as a I square because we have a standard result. I square is equal to minus 1. So you will get m square is equal to I square. So m is equal to 0 plus or minus I. Roots are pure imaginary. So yc of x is equal to c1 cos x plus c2 sin x. Now let us suppose that y is equal to a y1 plus b y2 be the solution of ordinary differential equation. Means we are supposing this equation, right? This as a solution. So here we need to find here a and b. So what is a? So we have a is equal to minus integration of y2 phi of x divided by w with respect to x, and p is equal to integration of y1 phi of x divided by w and integrate this with respect to x. So first we need to find y1 y2 phi of x w, right? So here first y1. So y1 will be compare this with what here? Compare this with c1 cos x plus c2 sin x with this. So y1 will be cos x and y2 will be sin x. So y1 is cos x and y2 will be sin x, and our equation is y double dash plus y is equal to sec x. So this phi of x is what here? This sec x. Now we got here y1 as cos x, y2 as sin x, and phi of x as a sec x. Now w we need to find. So w is nothing but Wronskian. So Wronskian is equal to determinant of y1 y2 y1 dash y2 dash. So y1 is cos x, y2 is sin x, y1 dash is differentiation of cos is minus sin x, y2 dash is differentiation of sin is cos x. Now solve this determinant. So cos x is cos square x, sin x is sin square with a negative sign. So cos square minus of minus sin square, minus of minus means plus. So cos square plus sin square is equal to 1. So w is 1. Now you substitute. A is equal to minus integration of sin x. This is y2, and phi of x is sec x divided by w is 1, and integrate this with respect to x. So sin x minus integration of sin x as it is, we'll write this sec as 1 by cos 1 divided by cos x dx. So a is equal to sin by cos is tan. This negative sign is as it is, minus integration of tan x dx. So integration of tan x will be log sec x, and this negative sign will be as it is, plus add constant k. So I'll take this constant as a k1. So this is a. Now find b. So b is y1 phi of x. y1 is cos x, phi of x is sec x, and w is 1. And sec, we'll write this as 1 upon cos. So cos get cancels. Integration of 1 dx is x plus add a integration constant. Already we have taken k1. So take this constant as a k2. And we have assumed that y is equal to a y1 plus b y2 with a solution of this given equation. So a substitute minus log sec x plus k1 cos x, because y1 is cos x, plus b substitute, b is x plus k2 and y2 is sin x. So constant one side and other one side. So constant will be k1 cos x plus k2 sin x. Other will be minus this cos x with this. So minus cos x into log sec x plus x sin x. So this is our complementary function, and this is our particular integral. So this is required solution. Now move on to next example. Find the curve on which the functional integration from 0 to 1 y dash raised to 2 plus 12xy dx with y of 0 is equal to 0 and y1 of 1 is equal to 1 can be determined. Means here what is given here? F of x, y dash is given, and initial conditions y of 0 equal to 0 and y of 1 is equal to 1. So they have given. So using these two, find arbitrary constants and substitute these arbitrary constants in general solution. So we will get a particular solution, right? So first general solution we want. So here I is equal to integration from 0 to 1 y dash raised to 2 plus 12xy into dx. So f of x, y dash is y dash raised to 2 plus 12xy. This is our f of x, y dash, means it is a relation between x, y dash terms, right? This is y dash raised to 2 plus 12xy. Now Euler's equation, what we have? Dou f by dou y minus d by dx of dou f by dou y dash, means we need to find dou f by dou y and dou f by dou y dash. So dou f by dou y will be differentiate this partially with respect to y. By differentiating partially with respect to y, keep other variable x and y dash as a constant. So we'll get this is constant, so this will be 0, and here 12x is constant, y with respect to y is 1. So we'll get dou f by dou y as a 12x. Similarly, dou f by dou y dash, this is equal to differentiate partially with respect to y dash, keep x and y as constant. So this is constant, this is constant, this is constant. So differentiation of this constant is 0. Y dash raised to 2 with respect to y dash is 2y dash. Now substitute this in Euler's equation. 12x minus d by dx of 2y dash. So this is dou f by dou y, and this is dou f by dou y dash. This is equal to 0. So 12x is as it is. D by dx of this y dash is y double dash. So 12x minus 2y double dash is equal to 0. Take 2 common. So you will get this as a 6x minus y double dash is equal to 0. Taking 2 common and sending this 2 to from LHS to RHS, 0 into something is 0. So we'll get this as a minus y double dash is equal to minus 6x. Cancel both minus, right, both sides. So you'll get y double dash is equal to 6x. Y double dash is nothing but what here? D square y divided by dx square. So d square y divided by dx square is equal to 6x, and we want y. So we want here y. So our objective of this example will be what here? For y. We need to find here y. So we want y. So for that you integrate this 2 times. You integrate this 2 times. So integrating first time. So integration of d square y divided by dx square is dy by dx. This is equal to 6 is there. X with respect to x. Integrate x with respect to x. So how it is like? Integration of x raised to n with respect to x. So this is x raised to n plus 1 divided by n plus 1. So here n is 1, 1 plus 1 is 2. So you'll get here as 6 into x square by 2 plus c1. 2 ones are 2 threes are. So dy by dx is equal to 3x square plus c1. Now we want y. So again, once again you integrate with respect to x. So y is equal to 3 is as it is. X square with respect to x. Integrate x square with respect to x. So this is x cube divided by 3 because n is 2. 2 plus 1 is 3. So x cube divided by 3. C1 because integration of constant will be constant into x. So C1 is constant into x plus we need to add the integration constant. So I'll take this integration constant as a C2. So y is equal to x cube plus C1x plus C2. So this will be the general solution. So first find here constants, arbitrary constants C1 and C2 by using the conditions. What we have conditions? Y of 0 is equal to 0 means y is equal to 0 at x equal to 0, and y of 1 is equal to 1 means y is equal to 1 at x is equal to 1. So use these two conditions. So using first condition, so in place of x and y, 0. So here 0, here 0, here 0 and plus C2. So 0 is equal to 0 plus C2 means C2 is equal to 0. So we got. And similarly, in place of x, you substitute 1. So 1 is equal to 1 cube is 1. 1 plus C1 into 1 is C1 plus, and C2 is what here? 0. So 1 is equal to 1 plus C1. We want C1. C1 is equal to, take this 1 to this side. 1 minus 1 is 0. So again you will get here C1 as 0. Substituting these two C1 and C2 in general solution. So y is equal to x cube plus 0 plus 0. So y is equal to x cube is the required solution. Now move on to next example. Solve the variational problem delta of integration of 0 to 1 x plus y dash raised to 2 dx. This is equal to 0 under the conditions y of 0 is equal to 1 and y of 1 is equal to 2. Now let I is equal to. So here compare this with what here? Delta I is equal to 0. In place of I, what we have here? Integration from 0 to 1 x plus y dash raised to 2. Integrate this with respect to x. So this is I. Now we have delta I is equal to 0. So this is equivalent to Euler's equation. So dou f by dou y minus d by dx of dou f by dou y dash, this is equal to 0. So we need to find here dou f by dou y and dou f by dou y dash first. So let us, what we have, f of x, y, y dash. It is a relation. So relation between x, y dash. So this is x plus y dash raised to 2. So now differentiate partially with respect to y and with respect to y dash. So dou f by dou y is equal to, so here with respect to y, this is constant, this is constant, so both are 0. So 0 plus, and differentiation of this y with respect to y is 1 plus 0. So you will get this as dou f by dou y as 1. So similarly dou f by dou y dash, so this is equal to 2 y dash, because this is constant 0 and this is constant 0. Differentiation of y dash raised to 2 is 2 y dash. Now you substitute these two in Euler's equation. 1 minus d by dx of 2 y dash, this is equal to 0. So 1 minus 2 is constant, d by dx of y dash is y double dash. So 1 minus 2 y double dash is equal to 0, or 2 y double dash is equal to 1, or y double dash is equal to 1 by 2, or y double dash is nothing but d square y by dx square, this is equal to 1 by 2. Now integrate with respect to x twice because we want y. So integrating first time, so you'll get this as dy by dx is equal to integration of this 1 by 2, means it is a constant with respect to x is 1 by 2 into x, and add integration constant. I will take this integration constant as a c1. So dy by dx is equal to 1 by 2 into x plus c1. Now integrate once again. So integration of dy by dx is y. This is equal to 1 by 2 into x with respect to x is x square by 2, because here integration of x raised to n with respect to x is x raised to n plus 1 divided by n plus 1. So x is n is 1. So x raised to 1 plus 1 is 2. So x square divided by 2 plus integration of constant is constant into x, and add integration constant as c2. Now we have general solution as y is equal to x square by 4 plus c1x plus c2. So this is general solution. Now use the conditions. So what we have, y is equal to 1 at x equal to 0, y is equal to 2 at x is equal to 1. Now use the first condition. So 1 is equal to x0 and x0. So 0 plus 0 and c2. So c2 is equal to 1. And use second condition, y is equal to 2 at x is equal to 1. So wherever y is there, replace 2. Wherever x is there, replace 1. So we'll get here as y is 2 and x is 1. 1 square is 1. So 1 by 4 plus x is 1. So this is c1 plus this c2. So simplify this. What we have c2 as 1. So substitute. So c1 is equal to 2 minus c2 minus 1 by 2. So substitute c2. c2 is 1. So c1 is equal to 2 minus 1 minus 1 by 4. So simplify this. So you will get c1 as a 3 by 4. So substitute this in general solution. C1 is equal to 3 by 4 and C2 as a 1. So y is equal to x square by 4 plus 3 by 4 into x, C1x in place of C1 3 by 4, in place of C2 1 plus 1. So what we have here, particular solution as y is equal to x square by 4 plus 3 by 4x plus 1. Now take, if you want further simplification, take LCM. X square plus 3x plus 4 divided by 4. Take this 4 to this side, from denominator comes this side, means here numerator. So 4y is equal to x square plus 3x plus 4. So this will be the required solution. Now move on to next example. Solve the variation problem. Delta integration from 0 to pi by 2 y square minus y dash raised to 2 dx is equal to 0, and conditions y of 0 is equal to 0, y of pi by 2 is equal to 2. So compare this with delta I is equal to 0. So here the I is integration from 0 to pi by 2 y square minus y dash raised to 2 dx. We want f of x, y dash. So f of x, y dash is y square minus y dash raised to 2. So we have Euler's equation. So dou f by dou y minus d by dx of dou f divided by dou y dash. This is equal to 0. So dou f by dou y means differentiate f partially with respect to y, keep other variable x, y dash as a constant. So here we don't have here x term, so y dash we have. So differentiation of this constant is 0, and y square with respect to y is 2y. 2y minus 0 is 2y. So this is dou f by dou y. So this is equal to 2y. Dou f divided by dou y dash, differentiate partially with respect to y dash. So while differentiating partially with respect to y dash, keep x and y as constant. So differentiation of constant is 0 minus 2y dash. So we'll get this as 0 minus 2y dash is minus 2y dash. Dou f by dou y dash is equal to minus 2y dash. Now substitute these two in Euler's equation. So 2y minus d by dx of minus 2y dash. This minus into minus is plus, and 2 is common. So taking 2 common and sending from LHS to RHS, so you'll get 0 into something as a 0. So we'll get here as 2y plus d by dx of this y dash is y double dash. This minus into minus is plus. 2y plus 2y double dash is equal to 0. So take 2 common and send this 2 from LHS to RHS. So you'll get 0 into something as a 0. So left is y double dash plus y is equal to 0. Y double dash is nothing but what here? D square y divided by dx square, and taking capital D as a d by dx, so d square will be d square divided by dx square. So we'll get this equation as d square y plus y is equal to 0, and y is common, d square plus 1 into y is equal to 0. So we need to solve this for y. Now so here RHS is 0 means this is a homogeneous second order ordinary differential equation. So complementary function is the general solution. To write complementary function, so we need roots. So find the roots of this equation. So for that, auxiliary equation. So how to write the auxiliary equations? In place of d square, so take m square. So auxiliary equation is m square plus 1 is equal to 0. So m square is equal to minus 1. So minus 1, we'll write this as I square. So because we have a standard result, I square is equal to minus 1. So m square is equal to I square. So m is equal to plus or minus. M is equal to plus or minus I. So roots are pure imaginary. So real part is 0. So y is equal to c1 cos x plus c2 sin x. So this will be the general solution. Next we want particular solution. Why? Because conditions are given. So use the conditions. Y is equal to 0 at x is equal to 0. So this gives, so first this condition, using these conditions, so y is 0. So 0 is equal to c1 cos 0 plus c2 sin 0. In place of x 0, in place of y 0. So sin 0 is 0, cos 0 is 1. So you will get c1 is equal to 0. Now use the conditions. Second one, y is equal to 2 at x is equal to pi by 2. So 2 is equal to c1 cos pi by 2 plus c2 sin pi by 2. So here cos pi by 2 is 0 and sin pi by 2 is 1. So 2 is equal to c2 because sin pi by 2 is 1. So c2 into 1 is c2. So c2 is equal to 2 or 2 is equal to C2. So this gives C2 is equal to 2. Now substitute this C1 and C2 in general solution. So C1 is 0. 0 into something is 0. So you will get this as y is equal to 0 into cos x, and substitute C2 plus C2 is 2 into sin x. So 0 into something is 0. So you'll get this y as equal to 2 sin x. So this will be the required solution. Now move on to next example. Solve the variational problem delta integration of 1 to 2 x square y dash raised to 2 plus 2y square plus 2xy dx is equal to 0 under the conditions y of 1 and y of 2 both equal to 0. Now compare this with delta I is equal to 0. So I is equal to integration from 1 to 2 x square y dash raised to 2 plus 2y square plus 2xy dx. Now f of x y dash. So f of x y dash will be x square y dash raised to 2 plus 2y square plus 2xy. So Euler's equation is dou f by dou y minus d by dx of dou f divided by dou y dash. We need to find here dou f by dou y and dou f divided by dou y dash. So dou f by dou y is, so differentiate partially with respect to y, keep other variable as a constant. So here x square and y dash square constant. So this is 0, right? Next differentiation of constant is 0, and 2y square with respect to y is 4y, and 2xy with respect to y is 2x. So we'll get dou f by dou y as 4y plus 2x, and dou f by dou y dash as 2x square y dash, means differentiate partially with respect to y dash. So here y dash raised to 2 is 2y dash with x square. So 2x square y dash, and here 2 is constant, y is constant, differentiation of constant is 0. 2 constant, x constant, y constant. So 2xy is constant. So both these two are 0. So left with what here? 2x square y dash. So this is dou f by dou y dash. So substitute these two in Euler's equation. 4y plus 2x minus d by dx of 2x square y dash. This is equal to 0. Now 4y plus 2x minus d by dx of x square y dash. You need to apply here product rule. So 2x square as it is, differentiation of y dash is y double dash, plus 2y dash is as it is, differentiation of this x square is 2x. So simplify this. So we'll get here as 2x plus 4y, this 2x and this plus 4y minus 2x square y double dash minus x minus 4x y dash. This is equal to 0. Now 2 is common for all the terms. Take 2 common, x plus 2y minus x square y double dash minus 2x y dash. This is equal to 0. Now x plus 2y minus x square y double dash minus 2x y dash is equal to 0. Take this 2 to this side, 0 into something will be 0. So you will get x plus 2y minus x square y double dash minus 2x y dash. This is equal to 0. Now this is equal to, take this x, keep this x as it is. So other terms LHS to RHS. So you will get this as x square y double dash plus, because minus is there, comes this side, x square y double dash, and minus 2xy dash plus 2xy dash plus 2y comes this side, minus 2y, and x will be as it is. We are not doing anything to this x. Now see this one. So this is a Cauchy's linear differential equation. So this is Cauchy's linear differential equation, and to solve this means first you need to bring this Cauchy's linear differential equation in terms of second order ordinary differential equation. So for that, so substitute x is equal to e raised to t. So t is log x, and x y dash is capital D into y. X square y double dash is d into d minus 1 into y. So we have taken capital D as a d by dt. Now substitute this in above equation. D minus 1 into y plus 2 dy minus 2y is equal to e raised to t. So multiply this d to this whole term. So d square minus d and this plus 2d minus 2, because y is common for all the terms. Take it outside. So inside will be d square minus d plus 2d minus 2. Minus d plus 2d is plus d. So next step is d square plus d minus 2 into y is equal to e raised to t. So auxiliary equation is, now we have reduced this into linear differential equation. Now this is a second order linear differential equation. So this is a non-homogeneous linear differential equation. So solution contains two parts, particularly yc plus yp. So general solution is equal to yc complementary function plus yp particular integral. So to find complementary function, so we need a root. So for that, auxiliary equation is m square plus m minus 2 is equal to 0. So find the roots. So m is equal to 1 minus 2. So roots are real and different. So depending on this roots, so we will write the complementary function. So roots are real and different. So yc of this t is equal to c1 e raised to t plus c2 e raised to minus 2t. So this is yc. So find yp. So yp is equal to e raised to t divided by d square plus t minus d. Sorry, e raised to t divided by d square plus d minus 2. Now how this is? This is of the form e raised to ax divided by f of t. So in place of a, what we have here? 1. So put d is equal to 1 in f of t. So this is a rule. So put d is equal to a in f of d. So in place of a, we have a 1. So put d is equal to 1 in f of t. So e raised to t as it is divided by 1 plus 1 is 2, 2 minus 2 is 0. So denominator is 0. Whatever method we applied, so this method fails. So our method fails. So we have to apply alternate methods. So yp is equal to, so t. So multiply this e raised to t with t divided by f dash d. So what is f dash t? Derivative of f of t. T e raised to t divided by d square plus d minus 2. So derivative of this will be 2d plus 1, because this constant will be 0. Again you substitute d is equal to 1 where? In f dash d. In f dash d. So you will get denominator as, numerator will be t e raised to t, denominator 2d. 2 into 1 is 2, 2 plus 1 is 3. So t e raised to t divided by 3. Now general solution y is equal to yc plus yp. So y is equal to c1 e raised to t plus c2 e raised to minus 2t plus t e raised to t divided by 3. So we need y of x. So substitute here e raised to t as x, e raised to minus 2t. So this is nothing but 1 upon e raised to 2t. So e raised to 2t. So we may write this as e raised to t raised to 2. So e raised to t is x. So you'll get e raised to minus 2t as 1 upon x square, and t is log x. So substituting all this in general solution, we will get y as c1x plus c2 divided by x square plus x log x divided by 3. So this is our general solution. Now use the conditions to find constants, arbitrary constants c1 and c2. So y of 1 and y of 2 both equal to 0. Y of 1 is also 0 and y of 2 is also 0. So y of 1 is equal to 0 means here at x is equal to 1, y is 0. So substitute. So we'll get here as 0 is equal to c1 plus c2. So this gives c2 is equal to minus c1. Now substitute y of 2 is equal to 0. So this means x is equal to 2 when y is 0, or at x equal to 2. So we will get y as a 0. So substitute this. 0 is equal to c1 into 2 plus c2 divided by 4 plus 2 by 3 log 2. Now substitute in place of C2 as a minus C1. So 2C1 plus 1 by 4 minus C1, because C2 is minus C1 we have taken, and plus 2 by 3 log 2. So 7 by 4, simplify these two. 7 by 4 C1 is equal to minus 2 by 3 log 2. So n log A will be log A raised to n. N log A will be log A raised to n. In the same way, 2 log 2 will be log 2 square. So 7 by 4 C1 is equal to minus log 2 raised to 2 divided by 3. So 2 square is 4. So 7 by 4 into C1 is equal to minus log 4 divided by 3. So C1 is equal to minus 4 log 4 divided by 21. So this is C1, and C2 is equal to minus C1. So you will get this C2 as 4 log 4 divided by 21. So substitute these two in general solution. So y is equal to minus 4 log 4 divided by 21 into x plus 4 log 4 divided by 21 into 1 by x square plus x log x divided by 3. So if you want further simplification, take this as a common and taking positive term as a first. So 4 log 4 divided by 21. So 1 by x square minus x plus x log x divided by 3. So I'll stop here only. Thank you.